Hey everyone, today we will be focusing on developing a full balanced tree, and without any further hesitation, let's get started. Now focusing on inserting a node into a balanced tree. So overall, first thing that we're going to do, as usual, is that we are going to include a library. So we're going to include iOS Stream, or depending on whatever IDE you use. We're also going to include algorithm. Then we're also going to include our header file that we made. TreePrinter.h, and then using namespace std. And so we'll have class. We're going to use this type of balanced tree called AVL tree. And then we're going to have a public instance right here. We're going to construct our node, where we will have a data point called key, and we're going to initialize the node on the left and the node on the respective right. And then we'll have int height, and then initializing the nodes as well with respect to the data point. Key of k, to the left null pointer, and then the right null pointer. Height already initialized as 1. Just gonna move this out. There we go. So putting that there. Now we're going to initialize our root, node root, AVL, and our class instance tree, starting with the root, and then null pointer. This is how we initialize first. And what we will do is that we'll have our height, get a balance, check the right side for insertion, and then check the left side for insertion. And then we will insert the node. So first thing we'll do is that we need to check the height. We can do so by having a integer function height, in height, node, with return node, or node with respect to height. There we go, and then we'll get the balance, int get balance of the following node with respect to the node, and then we will return a node or the following height of the node on the left, and minus the height to get to where we are inserting it. Here we go, and then we're going to check the right side for insertion. We do this by a rotation in this case, and I'm also going to put this right here just to, have it be quiet. So node right rotate for node of y. It's going to be node at x equals y at the left, and then node of t2 is going to be x at the right. X right is going to equal y once we are rotating on y left, will be equal to t2, and then we are going to get the height of our following max height, left. X with respect to the height equal max height x to the left. Then height x to the right, plus 1, and then we are going to return x. Yep, looks good. Now we're going to check for the left side for insertion. We're going to do this by left rotate. So node left rotate with respect to node of x. In that case, we're going node y is equal to x right, node t2 is equal to y left, y left is equal to x right is going to be t2, x to the height is going to equal max of the following height with x left, and then height of x right plus 1. Make sure parentheses are reset in place, and then we're going to have y's height equal max height with y left and a height of y right plus 1. And then we're going to return y. Now, next part, we will insert the node. We can do this by the following node function that we have. Node insert for node int key as the following parameters that we have. If there is no node, we're going to return a new node with a data point indicating that edge case, and then if the key is less than a node at the key for our insertion, we're going to insert at the left. Node left equals insert with node left key, and then else if the key is greater than the node key, that means we will go to the right and then insert the node at the right with the respective key as well. And otherwise, in our base case, we will return node and check the height. Right, and then get the balance as well, and check the balance of the tree. So check the height with the following node height to see if there's any adjustment. Equal 1 plus max of the height with node at the left, height node on the right. Get the balance by doing the following. Int balance equals the function we made for get balance of the following node. And now we're going to put in the Boolean conditions to check the balance of the following tree. If the balance is greater than 1 and the key is less than the node at the left with the respective data point of the key, then we're going to return right rotate of the following node. Then if the balance is less than -1 and the data that we have is greater than the node at the right data point, we need to return left rotate for the following node. And then in this case, for the next condition, if the balance is greater than 1 and the key is greater than the node at the left data point with respect to the key, we're gonna have nodes, the left node rotate with node left, and then return right rotate for the following node. And if the balance is less than, final Boolean condition, if the balance is less than -1 and the key is less than node to the right and the respective data point of the key, then we'll have node right equal right rotate with the right node. And we will return the left rotate for the following node as well. Finally return the node. In that case, now we will have our main function as well, after we made our AVL class. So the main function, the way it's going to be built out, is that we will have AVL tree, we'll call this AVL, and then we're going to call upon our TreePrinter and call this printer, as a following from our header file as well. Then we're going to have the AVL root. I have 3 instances of inserting avl.insert, avl.root with 10, and we're going to have other ones as well. 30. And then we're going to output nodes inserted into AVL tree and L and printer dot print pretty. Yep, we got that. We have AVL dot root. The initialize that, indent space 0, and we're going to return 0. Let's build this, see if this works. No matching case. And I was kind of afraid of this happening as well, so not to worry. There we go. And I also have the corrected TreePrinter as well in the following solution at the same time. So in that case, we would do that. But yes, this is inserting a node into a balanced tree. And now let's go over and try to figure out how do we remove a node from a given tree. Now, when we are removing a node from a balanced tree, we need to do the following. So we're going to keep everything that we did beforehand when it comes to inserting a node specifically in a balanced tree. The big key difference is, because we always need to check the balance consistently throughout the rest of the tree, is to do the following. So after we have done so, we need to create a min value holder to check the current node, and then we actually delete the node. So the way I'm going to go about this is have the node function node min value node with node in the parameter, and then node with the current node here. And while we are checking on the left hand side for the current node that we're looking for, setting a pointer, we're just checking our placeholder right now, and then return. Cool. Wait, okay. There we go. Set in place, and now we delete the node. And we do so by the following. Node delete node with the node at the root with respect to the key, and then if it's not the root, then we return the root as an edge case, and if the key is less than the root's data, which is root key, we'll go to the left and delete the node specifically on the root left side, it's data, and then else if the key is greater than the root key, we will go to the right side and delete the node on the respective right side key. And otherwise, what we will do is that if the root on the left is nothing right here, or the root on the right also has nothing, we're going to go down our following tree by having a temporary node, and then we're going to swap. So node temp equals root to the left, or root to the left with respect to the right. And if it's not the temp, what we will be doing is that we'll have the temporary be equal to the root, and then we'll have the root be initialized as a null pointer. Otherwise, we'll have a temporary root right here and set the following values accordingly. Finally, delete the temp, and else. In this case, we'll have a node temp equal the min value node from what we're getting on the right hand side, and then we will check for the key, the data really, and we'll also check over here on the right hand side, because we're looking on the left and then the right, delete node with root right and temporary key as well. And we're not done yet, so we also need another case where if none of the following root, we're going to return the root, and then we'll check the balance. Right. Check the balance as well. And we'll do so by the following. Root height equals 1 plus the max of the height with respect to the root left, and then height with respect to the root on the right. We get the balance. Since we're dealing with the balance tree, and we can actually just take from what we have done already beforehand, except we're going to not just return a node, but a root. So in this case, since we're putting in root, we'll do root to the left, replace the node with root, 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 Alright, so we don't have any errors there. And so what we're going to be doing is that we will now delete we will have avl root equal avl.delete node with avl root at a specific point, so we'll have 20. That means node has been removed from the tree. And then we're going to print out our updated tree as well. Just checking, and let's run this. There we go. Yes, that's what it does. It takes 20 from what we already did at the root, and it's going to place 30 at the following top at the same time. And so yes, this is how we delete a root specifically. Because we notice in particular that once we delete 20, we have 30 at the top, and typically the left-hand side contains key values that are going to be less, while the right side is going to be more typically, and so hence when we delete 20, 30 is replaced as a root, and we have done so accordingly. And so yes, this is how we remove and delete a following node as well. I will have these, so right over here, going through, we keep all the stuff that we did before, except for the differences is that we will have our we're focusing on the root to know exactly what to replace and what to actually set up and specifically delete at the same time. So yes, this was removing a node from the tree. Now we will move over to performing an in-order traversal. And now going over in-order traversal, the way we will be conducting such, it's actually really easy to be able to go over and know exactly what to put. Alright, so for in-order traversal, what I'm going to be doing, this is going to be the easiest function that we have, and we can also apply this for other ones as well. So all I'm going to do is void in order with node with root, and if the root is going to be in order, we check the left side. So we're implementing components of recursion as well. Root of key, we get that data point and we start outputting it right here. And then in order for the root on the right. And I'm just going to fix that. There we go. Here we go. And now what we will be doing is this. I'm going to all right, just double checking in this. So I'm just going to be doing avl.inOrder root over here, avl.root, in fact, I'm just going to say in order traversal. Let's run this thing. Build successful. Yep, that is correct. That is correct over what it does. We have the in order traversal already stated. In fact, I'm just going to put this right here. There we go. In order traversal is 10, 20, and 30, which is correct. It starts from the left, the root, and then 30 as well. So we already see 10, 20, 30 nodes. Okay, never mind. This, I should probably just like move this right over here. There we go. Okay, so we have in order traversal of 10, 20, and 30. Already stated before. And we also have selected node that has been removed, so that's just coming from over there. But really, yeah, this showcases in order traversal. And now let's head over to pre-order traversal. And now for pre-order traversal. Now pre-order traversal, we're just going to do the exact same thing that we did before for in order, except for the differences is just the ordering of the specific way we're outputting the nodes. Now, since we are treating each of the nodes with respect to the root and just using principles of recursion, we can just print out the root. So we will go void pre-order a node at the specific root, and if the root right here, we will go through the root key, and we will output the following over here, and we would use pre-order root at the given left, and then pre-order for the root at the given right. Just going up, checking to see everything. Yep, and so we check the current node in particular that we have over here. This is when after we have inserted the following, and then we're checking the left and the right. Heights as well. Yep, within our class. So pre-order is using the root to be able to actually check each node accordingly by setting the node as a root, and we're going through each order. It looks like we go through the root and the left and the right. So now for us to go through this pre-order traversal, what we gotta do is avn.pre-order. Yep, looks good over here. Let's run this bad boy. Yep, that is correct. Pre-order traversal. Hang on, let me just there we go, that's better. Yep, that's correct. Notice how we go from the root already, then the left, then the right. That is how we do pre-order. And now let's do post-order. And now we are going over post-order. So post-order traversal, again, we're going to apply the same principle that we did before. So this is the void post-order node for the root. And then if we're at the root, post-order root at the left, post-order at the right, and then count root key right here. There we go. And now we're going to do the exact same thing we did before. Make sure you spell everything correctly. Post order, ABL, post order. There we go. Make sure it's all corrected right here. Sorry, post order right here, post order down here. Yep, that is correct. That is correct. So we have post order already set. So we have pre-order. Post order function is already set up in place. We see 10, 30, and 20. That is good. 10, 30, and 20. That is the nature of the post order. It goes directly based on the levels, really. Left, right, and then to the root. Works its way up. Pre-order focuses on the root, leftmost, rightmost, and in order it goes from left, root, all the way up to the root, and then to the far right. And so yeah, that was post order. Now let's head over to breadth first search. Right here. And now focusing on breadth first search. So breadth first search overall is a type of search technique where we are actually searching throughout the entire tree, but we are focusing on the levels per se, starting from the top down. So say for instance we have our following tree that we have with 20 as the root, and we have 10 and 30 accordingly as its children. Now for breadth first search, it will scan through the rest of the tree, but really it's going through each level. So it starts from 20, goes from the leftmost node to the rightmost node, and it goes based on levels. So imagine that there are circles really circling from the top all the way down from the left to the right that are being drawn in this type of fashion. So that is the best way of describing breadth first search. Goes down by level. And so we will be able to replicate this by doing the following. So let's do our function BFS right here for including the node and its root. And mind you, there's a key difference that makes breadth first search, is that breadth first search uses a queue, which means we will go back up to what we've already done for this balance tree, and we're going to include the queue for the STL library. And we'll be doing the following. So we'll be checking in particular and searching throughout our root. We will return and initialize our queue using a node. And we will push all the instances whenever we are visiting each node and putting inside of our queue by using the push function, also known as the enqueue. And so while the queue is not empty, we will have a node set up to the front because queues go first in, first out, and we'll output the node's data by going node key and putting in spaces accordingly. Then we're going to pop the queue indicating that we've already visited, and if the node to the left is where we're at right now, we're going to push the information of the node that is at the left into our queue. And then we'll do the same thing for the right, check both the right and the left because we're already checking the root, and keep searching throughout the rest of the tree using breadth first search. So I'm going to double check. Looks like it's all good. Now we're going to output our breadth first search function by doing the following. Breadth first search for this, and we would go breadth first search AVL root. Let's build this, make sure it's all good. All right, let's run this bad boy, and does the same thing. Ready to go right here. Yep, it does it. So we have our tree 20, 10, and 30 as what we've already inserted. And kept everything organized. And then we have breadth first search accordingly. Go from 20, 10, and 30 in that case. Going through each level, having those imaginary circles per se, going from the top all the way down to the bottom, at the leftmost to the rightmost. And so let's move over to depth first search. And now focusing on depth first search. So depth first search, as the name suggests, or states, focuses on traversing and searching through a tree within the depth mode. So we're going to start with our root, but then we're actually going to go from leftmost depth all the way back to the rightmost, sort of like a giant circle per se. So depth first search would go to the leftmost and then goes to the right, outputting the following. So I also did a test beforehand, just to be able to clarify. So if we have a following tree, right here, if we have 20, 10, 30, there's like this giant circle that it's already going through from the leftmost, and it'll also go to the other subtrees as well, to the right. And depth first search is would be considered in that case. So breadth first search versus depth first search, there are key distinctions between the two. So breadth first search, we can imagine little circles right here going through each level, but depth first search is a giant circle going to the leftmost all the way to the rightmost. And so the way we're actually going to construct depth first search, another key distinction, is that breadth first searches also use queues, but depth first search use a stack to keep track of everything. And as we know before from our previous videos, that stacks are can be considered a stack of plates where it's last in, first out. And that's just a general principle to keep in mind. So the first thing we're going to do, we're going to include the library of stacks called include stack. So we have to call that from the STL library. And so we're going to be focusing on def for search by doing void dfs, and then I'm going to take the root as a parameter, so node root. Then if we're not at the root, we will just return just to initialize, and then we're going to initialize our stack with stack node for s, and then we're going to push our stack with the root as a parameter, so we go through continuously, and while stack is not empty, we'll have node equal s.top, indicating that we're going to have the node at its given top, and we're going to output the following data by doing count node key, indicating the actual data of the specific node, and put it in the list accordingly. Then we're going to pop the stack so we can go through each component of data. And if the node is particularly at the right, we will push the information of the stack on the right hand side, and the order is very critical, so that way we actually can replicate the nature of it. So right here, node left. For beforehand, def for search start from the left then to the right, where in this case within our function we go from we have right and left accordingly, just to push everything already set in place. And so I'm going to go down for def for search, similar to ref for search functionality. Def for search of the balanced tree, def for search AVL root. Let's just run this bad boy, see if it goes through. And yes, it does. It does go through. So we have the following tree that we have. Then we have the following outputs, 10, 20, 10, and 30. It goes through in a big circle, and we have similar outputs because of the size of our tree, namely. So we have 3 points. So just for general context, def for search uses stacks, ref for search uses queues, and def for search can be thought of as like a big circle that starts from the root and goes all the way down and all around. And ref for search can be tiny circles where we start from the root and go from the leftmost to the rightmost. So just a few things to be able to describe and communicate on. Now let's head over to unbalanced trees. And prior to going over our unbalanced tree, let's just go over the full structure that we have already developed. So we included our TreePrinter header already, and then we have our main class as well, focusing on the balanced tree that we have already made. We focus on the structure of the node, and then we've initialized our height, get a balance. We rotate the right and the left to ensure the balance of the following tree. We did insertion, as stated over here. We've also checked the balance as well after we've inserted, and then we also removed a node, and we also deleted a node, and thus checked the balance as well after we deleted a node. Another protocol we need to do. We performed in order, pre-order, and post-order traversal, breadth for search using a queue, and depth for search using a stack, making sure that we are still using the balanced tree, and we have the following outputs as well. So this is just a general overview from what we have already covered for a balanced tree. Hey everyone, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions or suggestions, please put them in the comment section. And as always, take care. Cheers. Bye-bye.